Welcome everybody. Today we've got a treat especial. Mengdi here from Carnegie Mellon's going to tell us about Mirage, which is this really cool super optimizer for tensor programming workloads. So we can get incredible optimization across a wide range of hardware targets. There's some very interesting techniques for reasoning about equivalence and doing optimization throughout this stack. So with that, Mengdi, please take it away.
Thanks for the introduction. So I would introduce our work on how to optimize the tensor programs for GPU kernels using superoptimization techniques. Okay, so GPU is a very popular domain-specific hardware, especially for executing machine learning applications. And its use is a very complex hierarchical architecture. And I would introduce it a little bit. So in each single GPU, there are tens to hundreds of compute cores, which are called streaming multiprocessors. And in each streaming multiprocessor, there can be hundreds of CUDA cores. And all these compute units can run in parallel, which lead to a very complicated design space of the parallelization strategy. Moreover, the memory at different levels have different bandwidth, sizes, and accessibility. Generally, a memory at a lower level has a higher aggregated bandwidth and a smaller size, and can be available by a smaller set of compute units. For example, the shared memory can only be accessed by the CUDA cores within a streaming multiprocessor. So in order to achieve a high performance, the programmers need to carefully manage the tensors at the different memory levels. So it is very hard for the programmers to design high-performance GPU kernels. And existing systems launch separate kernels for individual operators. For example, here, in order to execute this computation graph, the existing frameworks, such as PyTorch, would launch separate kernels provided by the vendor libraries for each operator, such as the RMS-ORM kernel, softmax kernel, and the matrix multiplication kernels. But this may lead to suboptimal performance due to the missing optimizations, including kernel fusion, algebra transformations, and local memory reuse. So in order to achieve extreme performance, people manually implement the optimized kernels for certain computation patterns. For example, here, the last three operators, matmul, softmax, followed by another matmul, form the very popular attention commutation. So people manually implement the optimized kernels, optimized attention kernels with like thousands lines of C++ code in CUDA or hundreds lines of Python code in Triton. And the remaining operator, RMS-ORM, is computed in a separate kernel. And this requires a large amount of human effort. So in order to achieve a balance between the human efforts and the performance, we introduce Mirage, a multi-level super optimizer. Mirage is not the first super optimizer or automated optimization framework. Existing super optimizers, such as Tensor and PET, apply algebra transformations on operators at the kernel level to find a better algorithm. And other category of work, including TVM and Answer, they perform scatter transformation to improve the efficiency of individual kernels. And all these works rely on the users to define the computation of kernels and cannot generate custom kernels whose computation is not standard. So Mirage uses a holistic approach to perform the optimizations across multiple levels of the GPU hierarchy and support all of the algebra transformations, scatter transformations, and custom kernel generation. And the input of the Mirage is a tensor program, and the output is a set of GPU kernels to efficiently execute the input tensor program. Mirage requires less engineering effort, while the users, instead of writing thousands lines of CUDA code or hundreds lines of Triton codes, they only need to write a few lines of Python code in Mirage. Mirage also achieves a better performance than the existing systems by up to 3.3 times in our benchmark. Moreover, Mirage does not rely on the manual implementation and can be easily adapted to new models and new hardware features. Okay, in order to achieve the holistic optimization, we first introduce our IR µGraph, a multi-level graph representation. So µGraph is a graph-style representation, which means we use vertices to represent tensor computation, and we use edges to represent the intermediate results. Moreover, Mirage would capture the hardware memory hierarchy using different types of graphs to represent the computation at different levels. Specifically, in a single µGraph, there can be a single kernel graph, where the vertices represent the computation of a single kernel running on all the M's of a single GPU. And the edges represent the intermediate tensors in each device memory. And the vertices here can be standard tensor operators, such as matrix multiplication or reduce, and they are supported by vendor libraries. Or if you want to fuse operators to achieve high performance, we can have these graph depth operators. They represent customized kernels whose computation is defined by a lower level graph, which are called thread block graph. So each thread block graph is associated with parameters such as grid dimensions, input and output mappings, and for loop mappings to represent the parallelization strategies. And similar to the kernel graph, we can also have this customized this graph depth operators, which represent customized thread block level operators, whose computation is by an even lower level graph called thread graph. And in a thread graph, the vertices represent computations running on each CUDA core and on each thread, and the tensors are stored in the register files. So with this µGraph, we are able to capture the optimizations at multiple levels. So next, I would introduce how do we explore the search space. Okay, so a common approach is to define a set of transformation rules that maps a subgraph which matches a certain pattern into an equivalent one or optimized one. For example, the first rule here represents the commutativity between division and matrix multiplication to reorder the two operators. And the second rule here applies the for loop along the reduction dimension of a matrix multiplication. And this is a scatter transformation. So this transformation-based approach is easy for optimizations within one level, because here the transformations can be summarized as limited rules. However, when we consider the optimizations across multiple levels, such as customized kernel generation, the problem will become hard. Basically, on the input side, since we can fuse arbitrary operators into a single kernel, which means there can be infinitely many possible patterns. And on the output side, we don't have the common rules to generate customized kernels, and therefore the transformations for customized kernels generation are dense and irregular. And it is hard for us to design the transformation rules for like these optimizations across multiple levels. So Mirage instead uses an exhaustive search. It takes as input a tensor program and uses an exhaustive search to generate all the possible µGraphs up to a certain size using exhaustive search. The generated µGraph candidates are not guaranteed to be correct. So the next component is equivalence verify that checks whether the generated µGraphs are functionally equivalent to the input tensor program using random testing with theoretical guarantee. And all the verified µGraphs are sent to the µGraph optimizer to perform optimizations that do not affect the correctness of µGraphs. Finally, the kernel with the best performance would be selected. Next, I would introduce the µGraph generator. I'm not sure whether we have a QA part or.
I think if you have like a, how long is your talk, Mengdi?
I think it's about 30 minutes.
That should be fine. You have plenty of time.
Okay. So yeah, feel free to jump in with any questions. Okay. So the next part is the µGraph generator. So in Mirage, we'll maintain the operators at all the kernel, thread block, and thread levels. And we use an exhaustive search to explore all the possible AST. For example, here we start from the input tensors A, B, and C, and tries to iteratively add operators into a µGraph. For example, the first operator can be a matrix multiplication, it can be an exponentiation, or it can be a graph depth operator. And the next operator can be, if we follow the first branch, the next operator can be another matrix multiplication. Or if we encounter a graph depth operator, we will try to generate its definition by recursively generating a thread block graph, a lower level graph. Yeah. So in this way, we do not miss any optimization opportunities captured by the µGraph representation. However, the search space would be extremely large. And our idea is to use expression-guided pruning. From the input tensor program, we can derive the desired expression we want to compute. Here, the computation graph is RMS1 followed by a matrix multiplication, and the desired expression is like this, showing as zk. And in this example, so during the search, we can use this desired expression information to guide the pruning. And in this example, the first branch computes the e to the power of xi. And the second branch, in the second branch, we insert a matrix multiplication. So the expression is summation over wki times xi. And in the first branch, we find that we compute an expression including e to the power of xi, which means all the following branches must have this expression as a sub-expression. And here we have assumption that in the optimal µGraph, there cannot be any redundant computation. So which means this e to the power of xi cannot be cancelled by the following computation. Therefore, we know that from the input desired expression, there is not any exponentiation commutation. So in this branch, since in this branch all the expression have e to the power of xi as a sub-expression, we know that this branch cannot find any valid commutation. So we just prune it out. And in the second branch, this yk is not directly a sub-expression of ck. However, it is actually a sub-expression of ck up to some algebraic properties. For example, we can reorder the summation over wki in order to make yk a sub-expression of ck. Yeah, and actually, it is possible for us to find an expression that is equivalent to zk within this branch. So in this case, we can keep the branch and continue exploring it. So these expressions provide good hints for pruning. However, full information expressions are still too complicated to reason about. And our idea is to use abstract expression. And the key idea here is that it is to abstract away the index details. For example, the matrix multiplication computation can be represented by summation over k, and the operators are aik times bkj. And the abstract version is summation over 64 elements, and each element is a times b. We can derive the abstract expression by recursively computed from the µGraph. So with this abstract expression, we achieve a good balance between the pruning quality and pruning overhead, because these abstract expressions can capture most of the semantic information and are easy to reason about. And how do we reason about abstract expression relations? We use eGraphs. So we define a set of interpreted functions for element level computation. We have addition, multiplication, division, exponentiation, square root, ReLU, and sum. We define a set of writing rules to represent the algebraic properties. Yeah, and here is the pipeline of our abstract expression guided search. We have two steps, the pre-process and the exhaustive search. So in pre-process, we take as input the input tensor program, and we derive the desired abstract expression from the input tensor program. Next, we build the eGraph for the desired abstract expression. And during the exhaustive search, in each step, we would check whether we want to prune this branch or not, using this abstract expression guided pruning. So in each step, we would derive the abstract expression for the current partial µGraph. And we look up these expressions in the eGraph. So if it is contained in the eGraph, then which means it is a sub-expression of the desired one. So then we just continue the search. Otherwise, we would prune it out. And the next step, next I would show some profiling results. So our results show that this abstract expression can significantly improve the scalability. And here, in this figure, the x-axis is the maximum number of operators we support in a third block graph. And the y-axis is the search time in minutes. And we can see that with the abstract expression pruning, in this benchmark, the search can consistently run within several minutes. But without abstract expression, we can only get first the search time grows exponentially, and we can only get the results within an affordable time for only 6 operators. And in this example, we require 11 operators to find a solution, to find a valid solution. So, which means this abstract expression pruning is necessary. Yeah, and this is for the first component, the µGraph generator. And next, I would go to the equivalence verifier. And the equivalence verifier, in Mirage, we support 2 types of verifiers, the probabilistic verifier and the formal verifier. And these two variables have their own strength and weakness, and the users can choose which one to use based on their workloads. The probabilistic verifier, so the probabilistic verifier only supports the lax µGraphs. I would introduce that lax definition later. and it is only supported in some hardwares. So basically, we need to implement a new probabilistic verifier in new hardwares, and we ensure completeness for it and imperfect soundness. And for the formal verifier, we can only support the µGraphs that can be encoded. And they can run in any hardware because we only need CPU. And we don't have completeness guarantee for this formal verifier, but we ensure soundness. And first is the probabilistic verifier. We use random inputs in finite fields to examine the µGraph equivalence. So here G1 is the input tensor program, and G2 is the optimized µGraph generated by the µGraph generator. We randomly sample the entries for the input tensors and evaluate them on both of the two µGraphs. And we check whether the output are equivalent. So we have completeness and soundness theorem. The completeness theorem says if these two graphs are equivalent, are functionally equivalent, then the output must be the same. And the soundness says if these two graphs are not functionally equivalent, then we can bound the error rate. So the completeness theorem is straightforward. And for the soundness theorem, it is motivated by the polynomial identity testing. So basically, for the polynomial identity testing, it is based on the Schwartz-Zipf lemma, where we can bound the error rate for random testing for polynomials. And here we extend the polynomial identity testing. We developed a new lemma to bound the error rate for the identity testing of exponential polynomials, which have this form. Yeah, and the next is the formal verifier. In our formal verifier, we encode the µGraphs into tensor level operators, and we build a set of writing rules and check the equivalence up to the writing rules using eGraphs. And in order to represent the parallelization strategies, we introduce these parallel operators. We have a partition, which partitions the tensors into along a dimension into multiple slices, and combines the reverse of it. And replicate means we replicate tensor along like a parallel dimension. For example, we can replicate a tensor along multiple streaming multiprocessors, and reduce is the reverse of it. Yeah, and to summarize this verification part, I would use a comparison between these two methods. So for the probabilistic verifier, we have the lax constraint, which means in the graph, we can only have linear division and exponentiation operators, and we can only have at most one exponentiation operators per path. This is from our extended polynomial identity testing lemma. And for the formal verifier, we can only support the µGraphs that can be modeled by the writing system. And for the probabilistic verifier, the time to verify is proportional to the model flops. And for the model formal verifier, the time depends on the graph size and the writing complexity. For example, for element-wise operators, the writing complexity is very low, and for matrix multiplication, we would have more complex writing rules. And the probabilistic verifier ensures completeness, and formal verifier ensures soundness. The probabilistic verifier supports imperfect soundness, and for the formal verifier, in our formulation, we cannot achieve the completeness by finite writing rules, because we find some cases that the completeness cannot be covered by finite rules. And for the portability, the probabilistic verifier currently is only supported for GPU, and will require new implementations for new devices. For example, if we want to extend Mirage to support like TPU or other accelerators, you need to implement new like this probabilistic this new random testing basically. Yeah. And for formal verifier, since we only require CPU, it can run in any hardware. Okay, and this is for the verification. And next part is our optimizer. So
Mengdi, I have a
Mhm.
question real quick. Do you have, and maybe you're getting to this, do you have sort of empirical data on when to use which verifier, or what their different strengths are in terms of how frequently I should use them?
Yeah, so my experience is that um, so you can only use formal verifier for new hardwares. So which means if you are targeting non-GPU architectures, then you can only use formal verifier. And this is I think this is the one of the major advantage of the formal verifier. And moreover, so the probabilistic verifier is suitable for the tensor programs who has simple arithmetic logic, but may have very complex tensor organization logic. And the formal verifier is on the other side. So the formal verifier can support maybe in terms of the arithmetic logic, it is complex. But for the tensor organization, such as tensor reshape, tensor transpose, so if the tensor program contains this complex tensor organization logic, then it's more hard for the formal verifier to verify, and it is more suitable for probabilistic verifier because the probabilistic verifier only only has this constraint on the arithmetic properties. Yeah, that's my experience.
Okay.
So actually, a related question is for the formal. So if I understand correctly, the formal verification here just means equivalence checking, right? Like you want to check.
Yeah.
So have you tried using a solver like a Z3 or something like that? And do you have any comparison between that and egg?
Yeah, I have tried this way. So, maybe this is too small, the font size. So, yeah, actually, we tried this way first, and we feel that it is very slow, especially compared to the probabilistic verifier, because the probabilistic verifier can run in GPU. Basically, it can run in parallel, so it is very efficient. And when we tried these three, we found that the solving time is very long compared to other methods. And when we convert to these eGraphs, the solve time is much faster than before and is comparable with the probabilistic verifier. But we need to redesign some of the writing rules because we may have some like I'm not sure whether this is because we do not understand the usage of egglog correctly. So basically, we may have some writing rules, something like we can partition tensor and combine it later. So this is equivalent to the identity function. And here we need to introduce new like parallel dimensions and parallel degrees. And yeah, in this case, we find that we have some difficulty when implementing this to eGraph. So we redesign it a little bit so that it can be represented in egg.
I see. It's interesting that maybe it's slightly, I'm not sure if it's actually obvious to me that the eGraph based formal verifier is faster than than Z3. But yeah, that's interesting.
Yeah, I guess there might be some implementation issues in this three. Uh,
So
uh,
Phil says something about vampire. Phil, do you want to?
Yeah, I have a bad habit of just doing stuff in chat.
yeah.
Yeah, I was just wondering, like Z3 maybe like lots of quantifiers and stuff isn't necessarily Z3's like strong point, and it's supposed to be the strong point of solvers more like vampire or eProver. And I always kind of wonder what if there's people who've tried really directly comparing these things more than my fiddling. So I just wonder if you could toss this into vampire. Also, I want where's this table come from? Where is this table of axioms?
This is designed by ourselves.
Okay, is it published in like I don't
Um, No, actually, so
okay.
cause it's not complete, yeah, because we find some cases in our formulation, we found some cases where basically it's about you can always partition along dimension and summation along this dimension. So, for example, you can do summation, partition, summation, partition. It is equivalent to summation over a dimension. So in this case, we can have infinity number of rewriting rules. So we don't think we have a good result for this set of axioms. So we do not publish it yet.
I see.
Yeah,
And that's why like the programmability of egg is that what's crucial here? That like there's some stuff that like if you had to encode it in a declarative format like SMTlib or Vampire's inputs, like you need to encode a bunch of rules that you can do very easily programmatically in egg. Is that what's going on here? Um,
I think that's a fundamental. So I think it's a fundamental issue of our formulation. So I think we can try this vampire or other solvers. But I don't think this completeness issue can be solved by using other solvers because I think that's an issue of the formulation. Yeah.
And you said, are you using, this is Saul, by the way, are you using egglog for this? And is that code open source?
Yeah, we use egg.
Egg or egglog?
Oh, we use egg, sorry.
Okay, thanks.
Yeah. Yeah, but I agree that we can try like this vampire because I think the redesign of the axioms is I mean introduce some implementation complexity in our development. So basically we need to rewrite some rewriting rules to be not human friendly. Yeah, so I agree that we may try we can try other solvers to make the program easier. Okay, and this is for the form verify. Yeah, thanks for the questions. I think that helped me a lot. Okay, and the next part is our µGraph optimizer, which is the last part. So in the µGraph generator, we only consider the optimizations that may change the semantic of the implementation, such as the algebra transformations, the kernel instantiation, and compute organization. So we separate all the other optimizations into the µGraph optimizer, such as this tensor layout optimization, memory planning, and operator scheduling. These optimizations are more orthogonal to the previous optimizations. So we do this to reduce the generated search space, and also for the for this µGraph optimizers tasks, they can easily be solved optimally. Yeah, and we evaluate Mirage on several benchmarks, and our baselines, including this vendor-provided libraries, expert-written kernels, and compiler-generated kernels. Yeah, and we have 6 benchmarks here. The first is normalized transformer. Second is attention with Q and K being normalized. So it's a larger benchmark than attention. And the third is RMS norm followed by a matrix multiplication. And next is group query attention, and LoRa, and gated MLP. And this is the relative performance on H100. The higher is better. We can see that Mirage can outperform existing approaches in most of the cases. And in normalized transformer case, Mirage is slower than the TensorRT baseline, basically. Yeah, and this is because TensorRT can directly load the tensor from device memory into regist file, so it can bypass the shared memory. But in Mirage design, yeah, we cannot do this bypassing. So that's why Mirage is worse than the best baseline.
So Mengdi, just a question about this graph. So you're showing the performance of the optimized graph, right? You're showing the performance of Mirage's output. Is that right?
Yeah.
Okay. Thanks.
Yeah, the orange shows the performance of the the best µGraph discovered by Mirage.
Yeah.
Yeah, and
thanks.
the blue, blue shows the best baseline performance. Okay, and this is the profiling results, the evaluation results. And next, I want to demonstrate that Mirage can discover hardware customized µGraphs using case study. So this is the µGraph for group query attention. Yeah, it is a little bit complex. So basically, here Mirage performed the commutativity. I mean, use commutativity between matrix multiplication and division to reorder these two operators. So yeah, recall that in the original tensor program, there's a division in the softmax and then followed by a matrix multiplication. And here we reorder these two. And we need we need two kernels here because we need to basically we need to communicate between thread blocks. So we need to use two kernels here. And this is like a parallelization strategy is similar to expert breaching implementations. And it's on L100. And we can see that on H100, Mirage can. So since H100 provides this GPC level or reduce, it allows us to have some communication between thread blocks. So in this case, Mirage automatically find a µGraph which only contains a single kernel. Yeah, and this kernel is 2 times 2 faster than the best existing kernels. And so I use this case study to demonstrate that Mirage can automatically leverage these new hardware features to optimize the tensor programs. And finally, I want to summarize. So Mirage is a multi-level superoptimizer which support these algebra transformations, spectral transformations, and new kernel generation. It requires minimal engineering effort, where the users only need to write a few lines of Python code, and it has high performance, which outperforms existing systems by up to 3.3 times. And you can check out our paper and our repo for more information. Okay, I think that's all for my presentation today, and I'm happy to take any questions.
Awesome. Thanks, Mengdi. Well, I have some questions, but let me see if other folks have any questions first. So one thing I was wondering, like, did you try to profile Mirage itself? Like, so there's 3 steps, right? There's the µGraph generation, there's the equivalence, and then the optimization. Like, which is the slowest part? And, like I'm curious about the eGraph parts, like how much time are they taking?
Yeah, the bottleneck is the generator part. Yeah, so actually previously we use this array for the abstract expression reasoning. So we model the writing rules as first order logic and use this array to reason about it. And that was slower than now. So current when we convert it to eGraph, we feel that it's much faster than before. I think one reason is because the eGraph implementation is faster, and also this rate, the SMT solver might be overqualified here.
Yeah.
And also for eGraph, we can pre-build the eGraph since say our sub-expression checking task is always about checking whether all the sub-expressions we encountered are sub-expression to the same final expression. So with eGraph, we can pre-build the final the eGraph, a single eGraph for the final expression, and we'll only need to do this checkup each time. So in this way we speed up the search by a lot. And right, Zach. Okay, so currently the bottleneck of the µGraph generator is about the parameter enumeration. So the grid dimensions, the input and output mappings. So basically, how do we design these parallelization strategies? Currently, we use exhaustive search for them, but that's very slow, and we will have an ongoing project to implement like this auto tuning style approach to speed up this part.
Makes sense.
I wanted to ask about abstract expressions because I saw some rules in there that from what I understand of it, seems like a really cool idea. And there's some of the rules that you had earlier in the slides. I was like, whoa, that's I just like, how do you think about them or what are they? Like, I'm assuming they sort of, you intend them to mean like sets of expressions. Like if I have an abstract expression A that like means some set of actual expressions, and you're reasoning about those sets is like my guess. And some of those rules like weren't, it's like an over approximation or something, maybe. There was one rule that was like, if you sum over sum I multiplication of xy, you can like move the summation in. And like that's like lifting y out as a constant, but that's not generally applicable. If I like read the 3 seconds, I could read that rule correctly.
Yeah, I agree. So do you mean that, for example, for some of the writing rules, they are So I think your understanding is much correct. So for this abstract expression, basically there are some so um yeah so we each abstract expression can correspond to a set of µGraphs. And these writing rules are overestimation, basically. So it means if a abstract expression is a sub-expression of the final one, which means this µGraph is possibly to be valid. And you are right that we may miss some pruning opportunity here. For example, this summation and division rewriting rule. So this is actually, so you can find some cases where an expression is a µGraph correspond to the expression on the left-hand side, and a µGraph correspond to an expression on the right-hand side, but they are not actually the same. So we miss information here. So basically, this is more I think this is more empirical design. You can have other formalization. For example, you can remove this reduction degree in the summation. in a summation operator. But our profiling results show that we don't prune enough in this way. So yeah, this design is to achieve a balance between the pruning quality and the pruning performance.
I see. Yeah, and I think like this isn't I'm not sure I'm not sure this is even like an abstract interpretation over like the like correct rewrite rules or something. It's like this is an equivalence relation that almost has a strange relationship with like the true. There's like you'd have an expression, you could abstract it to your abstract expressions, do rewriting on the abstract expressions. You could also
Yeah.
do rewriting on the true expressions with true rules. And I'm not even sure that those two like relationships even refine each other. So it's like kind of it's a cool thing that I can't really think of where I've seen something like this before. I don't know.
Yeah, I think one insight before this method is that the 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 translation from concrete expression to abstract expression is one way here. So basically, we get rid of the complexity between transformation between these two.
Right. Yeah, if something's true, if something's equal truly, it'll be equal in the abstract version, but not vice versa.
So it's a
Yeah.
sound over approximation, but the soundness is kind of up to the rewrite. Is it a sound over approximation?
It's the other way around.
Oh, so
Yeah.
I see.
I feel like there's something pretty strange about the directions of the arrows here. Because there's also the eGraph rewriting process itself is like you start with all these distinct terms and you're slowly like shrinking them to the true meaning eventually, like at infinity of like, oh, this actually represents the integers or something. And I think that the directions of the arrow, my intuition says the directions of the arrows here is like pretty odd, and not what an abstract interpretation would do. I think, but I could be wrong. This is pretty cloudy in my head.
One thing that this made me think about is the like hashing modulo alpha literature, where like you're concerned with like the equivalence of these terms with binders and stuff. And so like as a first take at it, you consider their shapes, where you replace all the, bound variables and binders with just holes, and you're only concerned about just the structure, like not the actual things that are in the holes. And that does feel like very much what you're doing with the abstract expressions, right? You're basically keeping everything but the bound variables. So I don't know if that's
Yeah.
useful, but that is a connection that it just made me think of.
Yeah, but I feel like she's also keeping, like you have to, if you forgot the variables, you could either throw out the rules that you need to know about which variables they are to actually apply those rules correctly, or you could just like apply the rules, even if you can't like disallow them. There's like the two things you could do, and it's the second version that is really interesting and unusual to my experience.
Yeah,
That you're like
that for
keeping the
sure.
rules, not throwing them out.
Yeah,
Um,
it's very interesting to see when people, and this is, yeah, Phil, you're right. This is a very interesting use case when people use eGraphs for like some funky notion of equivalence, right? That is like not exactly the one that you think of first, right? Like, is it some sort of over or under or approximation? Yeah, this is definitely an interesting use case.
I had kind of a follow-up question on that I asked part of when you came to the lab the other day. Just so did you try like using binders originally and making the rewrite rules like exact so it wasn't an approximation? And I think you'd said maybe you had some issues with that, and I was just curious if you could talk more about
Yeah,
that.
you are asking about why not just reason about the full information expressions? Is that your question?
Yeah. Yeah.
Yeah. So yeah, basically we have tried to also model this index informations, and we feel like it is very hard because it may introduce nonlinear computations, basically it may introduce this integer divisions, and we feel that they are very complex. So yeah, that's why we abstract them out.
Okay.
Yeah.
And
Where is the division coming from? Sorry, Saul, I just wanted one clarification.
Yeah, that's from like maybe let me I want to find an example, maybe okay, so no example. So for the output, basically, maybe I can use the final case study as an example. So in a output operator, the semantic of an output operator is to concat multiple tensors together. And if you think of the expression of this tensor O, then you need this derivation class. You may want to say something like OI equals something. Then if this O is from output tensor, so you can think of this output as a contact. So let's say if we have n slices for a tensor and we concat them together, then the expression of the output tensor is OI equals I divided by the slice size, like let's say B, I divided by B, and we need to take a rounding here.
I see. Okay. Saul, do you want to finish your sorry,
yeah, no, that was a good. This is kind of a follow-up on that. If you go back to the large set of rewrite rules you had with like the concat and stuff. So like, yeah, I noticed that. Mhm.
You mean you want to go to this page or?
Yeah, that one. Yeah. So like you have like equivalencies between like partitioning and matmul and like reducing and partitioning, but you don't have like a canonical form that you're necessarily going to. You just have sort of a number of equivalent forms. And I'm wondering if you considered trying to canonicalize the arrays operations in some way.
What do you mean by canonicalize the answers?
Rewriting in symbolic form where like both of those rewrites would reduce like to the same symbolic form.
I see. So I think it might be possible. I think the challenging part here is how do we define? So if you want to canonicalize something, basically you need to have some. So you need to have some steps to reduce the potential, something like this. And I feel like it's challenging to define the canonical steps here. Yeah.
Thank you. Yeah.
I had a question about your µGraph design. So I think there's like two parts of this that's really cool is like this abstract expressions. And I think it's also pretty cool from what I understand is that you're simultaneously searching over equivalent arithmetic expressions and where to execute those expressions. Like if that happens in a kernel or a thread block or I forget what you use, exactly the words you use. And so I wonder if you've thought about like extending this to a model where maybe you have multiple GPUs or you run part of it on a CPU and part of your µGraph is like searching over, because I know on like GPT OSS, I think some people will run the expert selection part on the CPU and then find that that's actually faster. So I wonder if you've thought about that.
Yeah, um, I think for the µGraph representation, it mostly utilize this SPMD semantic to reduce the representation complexity, basically. So if we want to have something run on CPU, basically if we want to have some like this heterogeneous commutation, then yeah, we need to extend µGraph semantic.
Okay. Yeah, and I guess I was also wondering, like, so you mentioned in the beginning, there's some existing work on finding equivalent algebraic expressions
Yeah.
with like Taco, I think. And I was
Yeah.
wondering, like, to what extent, like, it's pretty amazing how successful this compiler is. Like, it's actually really awesome. And I was wondering, like, to what extent you think its success is due to like your being able to find algebraic expressions that aren't findable with existing methods, and to what extent it's like your search technique being able to simultaneously search over equivalent expressions and like different ways to run them.
Mm,
So
I
sorry,
think.
Mengdi, just sorry, before you answer, I have to go because I have another call. Is this
Mhm.
Zoom gonna be, Max, this Zoom is gonna stick around, be around, right? Like if people drop or
Yes.
okay, all right. Bye.
Okay. Yeah. So in terms of performance, I think we benefit from both. Yeah, actually, so we simultaneously consider abstract transformation and scatter transformation. And some scatter transformation can only be enabled after we apply some algebra transformation. So I think the part of our benefit comes from this joint optimization.
Cool. Thanks.
Okay. Well, I think we are at time. Thank you so much, Mengdi. Yeah, this was a great talk. And yeah, I will conclude the recording now.